All right, this is the homework help for section 6.5, and in this first problem, number 5, we are going to learn how to use the formula which tells us that the z-score is a particular mean x bar minus mu over sigma over root n. All right, the first question asks us this. Suppose that we have a population which has a mean of 8 and a standard deviation of sigma is 16. Now we're going to start taking samples out of here. Each one of these samples is going to have a particular size, n equals 64. And we're asked 4 questions about the way that these x bars look like if you were to take several samples, compute the mean for each one. These x bars would jump around. Some of those would be more than the mean of this distribution here. Some of them would be less. How are they distributed? So we've got several questions, or 4 questions rather, that are related to that. And here we go. So first of all, describe the distribution of the x bars. Well, these x bars are going to be approximately normally distributed. They are going to have an average value of mu, the same as the mean of the whole population. And the x bars have a standard deviation, or sometimes we say a standard error, of sigma over root n, the standard deviation of this whole population, but then divided by something. So it's actually getting smaller as the size of the sample increases, and a size of 64 is pretty big. Now this raises a helpful point to know about, and that is in the central limit theorem, we said that this will be true. The x bars will be approximately normally distributed if the sample sizes are large enough. So the question is, how large is large enough? Well, the answer to that is a little bit harder than it sounds, but generally speaking, if this original population doesn't have very much skew in it, then samples of up around size 30 are large enough to get this effect. If this starts normal back here, then a sample of size 1 is good enough to have this. But if this starts is something that's far from normal, but is not skewed and doesn't have outliers, then you can expect this to kick in by the time the n is up around size 30. On the other hand, if this original population is strongly skewed, then the sample size may need to be quite a bit larger than 30 before this gives reliable predictions. But it's hard to give a recipe for that in general. It depends a lot on the details of this back here. Generally speaking, though, in the absence of strong skew or outliers, we say that these kind of calculations are good as long as n is at least size 30 or more. So our size 64 is easily within that limit, and we're ready to go. So describing the distribution of the x bars, they'd be approximately normal, mean of mu, standard deviation of sigma over root n. Secondly, we're asked to find a z-score that corresponds to a sample mean of size 9. So the idea is we take out a particular sample, we compute the mean of this sample, and suppose that turned out to be size 9. Now notice that's a little bit bigger than the mean of the whole population. That can happen. Samples can vary a little bit from the what the population looks like. And the question is, can we get a z-score that corresponds to this x bar? And if we can, then we can use it to compute probabilities. So let's go after the z-score next. Okay, so here's our situation. We have a population with a mean of 8 and a standard deviation of 16. We have a particular sample of size 64. Its average or mean value is 9, and we want to find the z-score that corresponds with that. The way to do it is to use our formula right here. So z is equal to the mean of this sample, 9, minus the mean of the whole population, 8, over the standard deviation of the x bars. Well, that's not the standard deviation of the whole population, though it is related. It's 16 divided by the square root of the sample size, and the sample size is 64. Now we could do some of this calculation by hand in this case. 9 minus 8 is 1. And down here in the denominator, the square root of 64 is 8. 8 times 8 is 64. So we have 1 divided by 16 over 8. 16 divided by 8 is 2. And so the z-score is 1/2 or 0.5. And that takes care of the first question. The second question, after we've come up with a distribution, is this: find the probability that an x bar value will be more than 9. Well, this is hard to answer in general, but we can do this by translating this x bar to a z. That's the same as the probability that z is more than, well, if the x is 9, that's it right here. If the x is 9 for this sample size and coming out of this population, then the z must be 0.5. Now here we could look this up in a table, or we could use our calculator. Let's use our calculator in this case. We are going to be using the distribution function. Second distribution. We want a normal CDF. And there's various ways to use this. I'm going to use it in a way that's consistent with the table. And those of you who are more comfortable with your calculator know how to shorten this process a little bit. But this would be just like you'd use it on the table. What you'd say is we want to look at the z-score of 0.5, and we want everything lower than that. And this is 1 times e to the minus 10 to the minus 99. This is just going as far to the left as we can. Actually, you don't have to use a number anywhere near that negative, but this will be fine. The mean of the standard normal is 0, and its standard deviation is 1. Paste that in, and we get 0.69146, but that is the area to the left of z equals 0.5. So our normal distribution, standard normal distribution, looks something like this. 0 is here. That point of inflection would be right over 1. We are trying to get the area that's above z of 0.5. Now, what we've just computed with our calculator is the area that's below 0.5. So we've gotten this right here. And if you look up z equals 0.5 in your table, you'll get this number as well. So this is equal to 1 minus the area below. The area below, we just done with our calculator, 0.69146. And if we subtract that from 1, we get 0.30854. And that kind of makes sense, doesn't it? If we cut the area off here at 0, the area above would be half of the area. And so we have a little bit less than that, around a third. That's making some kind of sense. So we're saying that the probability that an x bar that is comes from a sample of size 64 out of this kind of a population, its probability of having a mean greater than 9 is only about 0.31. So that takes care of part C. I've labeled that as B. Here we go. It's part C, and now let's move on to the last part. Now finally we want to answer part D. Would it be unusual for samples of size 64 from this population to have a mean that is greater than 9? Well, there's a couple of ways of answering that question. And the first way I would say is, we just computed that probability. The probability that x bar is more than 9 is about 30.8 or 31%. So is it unusual? Would it be unusual for x bar to be greater than 9? Not really. That happens almost a third of the time. So we've already computed that probability directly. There is another way to answer that question, though, and that is we have a general rule of thumb that tells us this: with normal distributions, most observations are going to fall between about the mean and plus or minus 2 standard deviations. Well, the mean of the x bars we know is 8. 2.5, we just copy here, and then we want the standard deviations, but these are the standard deviations of x bar, not of the original population x. Well, we know the standard error of that. It's sigma over root n, and that's what goes in right here. Of course, we've already done that, right? That is sigma over root n right there, and we've already simplified that. That's 2. So we have 8 plus or minus 2.5 times 2. 2.5 times 2 is 5. So we have 8, subtract and add 5. Subtracting and adding gives us 3 and 13. So that tells us most of the x bars lie in this range from 3 to 13. Now, there are things in there that are more than 9, right? So would it be unusual for something, for an x bar to be bigger than 9? No, not at all. We're expecting them to fall within the range of 3 to 13. So whether you use this general rule of thumb, this guideline that we've had in the past, or you look at the particular probability that we've computed, you'd come up with the same answer. No, it's not unusual for the sample means to be larger than 9.